Digital transformation in manufacturing through Industry 4 is seeing us move at pace around connectivity. Connecting factories, processes and machines is key to us realising the productivity and sustainability agenda. Being able to link processes and products through digital twins and a connected digital thread is where we are going to see real impact in industry. When you put a manufacturing process like subtractive under a lens, the layers and depth of data opportunity become significant. If you want to couple data and modelling to enable autonomy, you will need multiple digital twins with data from a range of sources which will have differing use cases.
Data is a big part of Industry 4.0, and at the AMRC we're implementing and developing various digital solutions to collect synchronized high-speed data from our machines and sensing equipment. This data is highly valuable for the analysis and modelling work we do around subtractive, particularly for research and development towards autonomous machining using artificial intelligence, where we're looking at key research areas such as real-time tool-like prediction, fault detection, process dynamics, and so on. With this work, we are also trying to show the subtractive industry how they can exploit the benefits of acquiring all this data and move towards digitalization.
Here at the AMRC, we've developed a patent-pending X-ray diffraction-based method for non-destructively assessing machine surface integrity. The technique, which can be used for on-machine inspection, is capable of detecting and sizing anomalous surface integrity features such as white layers and plastically deformed layers, allowing non-destructive surface validation in a matter of minutes compared to the time-consuming and destructive microstructural cut-up method that is traditionally used.
In the cutting technology team, we create representative part geometries that capture the challenges of our partners' products while maintaining confidentiality. These representative parts replicate common features seen across multiple manufacturing disciplines such as aerospace, medical and defence. Driven by today's demands for complex, lightweight 5-axis part designs, they allow us to research common themes such as distortion, deflection and sequencing.
Virtual machining is a great tool for assessing tool class strategy, tool geometry and other machining parameters. It can reduce the amount of physical trials required for optimisation and provide greater confidence in the process. Simulation of cutting forces, chip thickness, power torque and part distortion give a strong indication of process quality and is a key stepping stone for process planning.
Modelling of machining operations at the chip formation scale is a key tool for optimising machining strategies and tool geometry. Here at the AMRC, we have developed finite element, analytical and novel rapid hybrid modelling methods to predict the chip formation in machining operations from orthogonal turning all the way to milling. Our models can predict the cutting forces, temperatures, the tool wear and the integrity of the machine surface with respect to the thermomechanical deformation and microstructural changes. A team of experts at the AMRC have successfully created a novel real-time digital twin framework for CNC machining operations. The testing was validated by a closed-loop control system. This was implemented across various machining applications and included a novel online machining-induced residual stress control system, tool chatter detection and adaptive feed rate control. We believe this digital twin toolkit is a huge step forward to predict and anticipate non-conformances in the process and take corrective action before it occurs. This is crucial within the machining sector to help achieve higher productivity, reduce costs and ultimately lead to more sustainable manufacturing processes.
At the AMRC, we focus on high-value manufacturing challenges. This means we need to understand the impact of a subtractive process at the material level. This is essential for high-performance applications. This will allow us to develop self-optimising adaptive processes capable of achieving zero defects, which will be certified through a digital passport. As we embrace Industry 4.0 and develop a greater level of process autonomy, we need to not lose sight of the human factor. Developing skills at all levels and understanding the interaction of autonomy and a future skilled workforce will be key to delivering an agile, subtractive manufacturing sector.